Hi there YouTube, my name is Nico and welcome back to my channel. In today's video we're going to look at how does sound work part 4, digital. Now of course, if you haven't already, please check out parts 1 to 3. Because we lay the groundwork of what we are going to be talking about today in this video. Now in part 1, we mentioned about how the sound actually transmit from one place to another place in the air. It's about exciting the air molecules so that they travel at specific frequencies, and we also mentioned that as the sound travels further and further, it gets attenuated eventually until nothing is left. We also mentioned that your lower frequencies tend to travel further and your higher frequencies don't travel as far. In the second video we talked about resonance and what happens when I have specific sounds loud enough. Can I affect a structure, yes or no? This of course comes from the infamous opera singers who break glasses with their singing voice. So, we tried to break a glass, unsuccessfully. However, in video number 3, we discovered what happens if I look at the cone of a speaker. Why didn't the glass break? And it's because the speaker cone has a specific angle to it. The sound is traveling in a wider angle, and if I can close the angle in tighter, I can actually focus the sound to where I want it to go. So in video number 3, we used a plastic cone, put it over a speaker and focused the sound with specific frequencies, of course, the resonant frequency of the glass, and eventually the glass did break. We reproduced that experiment again for a second glass as well, just to prove that we were correct in our assumptions. In today's world, we have all kinds of music reproductions, but all of it is digital. I mean, if you look at what is happening on this YouTube video, this video is sent to you via ones and zeros over the internet. The ones and zeros then get converted back into some other type of signal so that you can see and hear it. Now, particularly in terms of what you are hearing is a digital to analog converter, because the digital sound has to travel through the internet and then gets converted back into an analog sound. However, it starts out with my microphone. My microphone is an analog device that has to convert an analog signal into a digital signal, which I am currently recording. From there, the digital signal then travels through the internet and reaches you. From there, your computer or device, your tablet or your phone, wherever you're watching this video on, now has to convert that back into an analog signal, so that the speaker in your device or your home theater system or your computer can reproduce that sound, which has to be analog. So the question is, of course, how does that work? How do we convert an analog signal like this microphone into a digital signal? And then on the other end, how do I convert it back into an analog signal once it's traveled through? To demonstrate how to convert an analog voltage into a digital signal, I'm going to build a circuit and program a microcontroller. what's going into the resistor is 5.02 voltage. What's coming out of the resistor is very little, a few millivolts. So that means that the voltage is now going into this microchip, an analog voltage. And that analog voltage is now being converted into the digital signal that you can see over there. So for 0 volts, I have a binary code of 8 zeros. That is why each one of these LEDs are currently off. So what now happens if I start to increase the voltage? For instance, to there, I can measure what is now going into the microchip. And in this case, it is 1.472 volts. And that constitutes only 2 lights going off over there. If I increase the voltage even more, for instance over here, I now have a voltage of 2.550 volts. And I can now go and increase the voltage going into the microprocessor up to the full voltage, which in our case will now be the original 5.02 voltage. A little bit less. Okay. I downloaded the code from the internet, and we all know the internet doesn't lie.
Internet does not lie.
The purpose behind this demonstration was to make you understand what happens inside microcontrollers. Most microcontrollers have analog to digital converters built into them, and some have multiple analog to digital converters so that it can handle multiple signals at the same time. That is important because if you think about what happens in a home theater system, for instance a 5.1 surround sound system, you have 6 channels that has to be converted into a digital signal, and that signal then gets transmitted via an optical or coaxial or even HDMI cable. Once it reaches the amplifier stage, that has to be converted back into an analog signal so that it can be amplified and the speakers can reproduce the sound. So there you have digital to analog converters. Again, multiple digital to analog converters that converts at the same time. So what happens when we convert such a signal as an analog audio signal? Let's start with a few definitions. Frequency. That is the number of cycles a wave will travel in 1 second. It is measured in hertz. So what does a sound wave look like? And if you remember from our previous videos, it is like this sine wave as you can see on the screen. If the sine wave has 1 cycle that it travels in a second, that means its period takes 1 second to complete. The amplitude, of course, is how big is the wave. Now, the number of those waves in a second will equal the frequency. So if, for instance, if I have 50 of these cycles, as you can see on the screen, per second, the frequency will be 50 hertz. The next definition is resolution, and this is specifically as it relates to analog to digital converters or ADCs. Now the resolution is the number of pieces a sample is divided into. This is expressed in bits, which is an exponential expression for 2. For example, if I take 4 bits, that is 2 to the power of 4, which equals 16. That means a sample taken will be divided into 16 equal pieces. So if I take 4 bits, for example, and divide this sample sine wave that I have on the screen into 2 different parts, it will look something like this. So the first part is the positive part of the sine wave, and the second part is the negative part of the sine wave. Now, if I go to 2 bits, that means I will have to divide each one of these 2 halves into halves again. So I'm going from 2 to 4 pieces in the complete sample. So now I can divide it up like this. And if I go to 3 bits, I do division again, and each time I divide, I get a smaller part. 4 bits, I have 16 pieces in the sample. And this will of course increase as I go along. The center of each of these seconds actually represents the sine wave at that point. The sine wave travels through the center of the top of the rectangle. Part of the sample, however, is discarded. Because it is only a 4-bit sample at this stage, there will be pieces that does not match up completely with our sample. I've highlighted them in red. As you can see, they will not be converted properly into the digital signal. To decrease the discarded parts on that sample, we can increase the bit resolution. Every time 1 bit is added, the number of parts in the sample actually doubles. So for 5 bits, you will see I doubled the first half of that sample, for example. And if I look at the red discarded parts, you will see that it is much smaller now than in the previous 4-bit example. And let's move over to 6 bits and see what that looks like. The parts are now half of what they were in the 6-bit example. And as you can see, again, the red sections that are discarded is much smaller now. And with a 7-bit example, I increase that resolution even more, which means that the discarded parts is even smaller. So small, in fact, that you can't actually see it properly on the screen at this stage. Now, that means that the error is much smaller in a 7-bit example than in a 4-bit example. This is of course not nearly what we have with audio, for instance. In the examples of audio, we typically work with something like 16 or 20 bits and even sometimes 24 bits. So if you do the mathematics, you will see that the number of parts that a sample is divided into is actually extremely high, which makes the accuracy of converting the signal from analog to digital much more accurate, especially once it has to be converted back from a digital to analog signal. Our last definition, of course, is the sample rate as it relates to the analog to digital converters. The sample rate is the number of equal parts that a 1-second sound wave is divided into. And that is measured in hertz, not to be confused with the frequency, which is also measured in hertz. If you look at this 1-second example on the screen right now, you will see that even in just this 1 second that we have a whole lot of things happening over here. So if we look at this section of the song right now, this might be only a very, very, very small section in this case. So I could say, for instance, that I now have, let's say, this section over here. Okay, and that section in comparison to the 1 second that we have is now 0.0003 seconds. Now, that is a very small time, but as you can see, even in 3 milliseconds, a lot is happening. If I want to convert this signal to a digital signal, I'm going to have to be pretty precise in terms of my timing. Because remember, this little section is only 3 milliseconds. However, there's a lot happening in here, and I can only do one part at a time. So this is where the sample rate of an analog to digital converter comes in. It needs to take a snapshot of this in very small increments, smaller than 3 milliseconds, if it wants to reproduce this accurately. And this is where you get good quality and bad quality amplification and transmission of digital sound. When the sample rate is too low, it will not reproduce everything that you see. It might miss certain sections. Now, if you look at my screen over here, you will actually see that it has a sample rate of 44,100 Hertz. That means it is taking a snapshot 44,100 times a second. So I can take this whole second that we have over here, and if I divide it up into 44,100 equal parts, that is the sample rate. And that, coupled with the resolution of the analog to digital converter, gives you a quality sound. So those two together needs to be there so that you can have an accurate sound translated from analog to digital. Now, one thing to remember, of course, is once this sound is now converted from analog to digital, it transfers, for instance, from a CD player up to the amplifier, and the amplifier now needs to convert it back into an analog sound for the speaker to reproduce the sound. So after the ones and zeros get to the amplifier for transmission, it needs to be converted back into an analog signal, because a speaker doesn't understand ones and zeros. The speaker only understands current and voltage, because that is going to create the magnetic field that moves the speaker cone in and out. And that is why we need to have an analog to digital converter and then a digital to analog converter back so that the speaker can reproduce it. Now, we already mentioned that once I convert an analog signal into a digital signal, if my sample rate is not good enough and my resolution of the analog to digital converter is not good enough either, I'm going to lose a little bit of my sound quality. So, of course, the better the resolution is and the better the sample rate is, the better the reproduction of the sound is going to be. Of course, once it is converted to digital and it needs to be converted back to analog, you need that same quality. Otherwise, it is a compounding problem. If you have a bad quality analog to digital converter and then a bad quality digital to analog converter, I'm not going to lose once, I'm going to lose 2 times. So I hope you all enjoyed this video and learned something from it. This was, of course, only an introduction to digital systems, and hopefully we can take the series further into the future. If you have a comment or a suggestion, please leave it in the comment section down below. And if you haven't already, please subscribe to my channel and press the like button. Only about 25% of you are currently subscribed to my channel, so I hope you click that subscribe button. And until I see you in the next video, cheers.